Sounds good. Thank you.
Certainly not least in this session, our fearless leader, Steve McCandliss, and also
I really apologize for this. All the presentations are posted on Slack, so if it's easier just to follow along there, I encourage you to get a little higher resolution. We're going to talk a little bit about, I'm Steve McCandliss, research professor here at Johns Hopkins, director of the Center of Astrophysical Sciences. Paul Scowen is, what is your title?
Senior research astrophysicist
At Goddard, yeah, okay. And we're gonna talk a little bit about science enabled by Lyman ultraviolet capability and technical requirements and status.
The lab sheet.
Sir, I am a serial mutterer, so as my wife points out, so please, just nudge me. I think there's a big question mark on habitable worlds. I think that should be emphasized going forward. Work has been stolen from many people. And you've all seen this. If you haven't seen this, you've been asleep during the whole meeting. So, level 1's requirements for habitable worlds observatory is roughly speaking 25 isoearths within 100 parsecs or so. Oh yeah, and we're supposed to do transformative general astrophysics. Okay, so the themes of astrophysics are complex. How does the universe emerge from the indistinguishable? You have the emergence of particles, radiation, and structure, the emergence of elements, molecules, and dust. Ultimately, the emergence of life, and then the dust becomes us. But the question of habitation is not only local, it is universal and transformative, and ripping off of the old NGST tagline, I hope that habitable worlds will be visiting a time when galaxies came alive. So we'll see if that flies with anybody. General astrophysics themes for HWL worlds in context. Worlds and suns in context, and the priority area, of course, is pathways to habitable worlds and cosmic ecosystems, unveiling the drivers of galaxy growth. And to be transformative, I will argue that both themes require the Lyman UV down to 1,000 angstroms-ish and below 1150. So science in the LUV is spectroscopically driven, and that's because the geochronal Lyman alpha prevents us from really doing any kind of photometric studies below Lyman alpha. We usually have to have some sort of edge filter. There's a list of ionization species, high ionization, low ionizations, and molecular species that have been gone over in great detail over the past few days, and many science cases have been given great exposition over the science portion of the meeting.
And that's the Apollo image we were talking about.
This is, yes, this is a picture of, I'm sorry, Eric's phone is somehow in the way. I can't get rid of it, but it's this is a picture of Earth taken from the moon in Lyman alpha by George Carruthers electronic graphic camera on Apollo 16. As far as I'm concerned, this is my favorite image of all time. Better than the pale blue dot, because it's really blue. Okay. Sorry. So, of course, LUV observations of exoplanet life cycles have been detailed in the LUVAR report. And we've seen these examples throughout the week, as well as the LUV observations of cosmic ecosystems. I would point out that quasar absorption line spectroscopy really gains with the size of the mirror. The number of objects that you can get down here, this is more B, gets to be about 500 or so quasars in the sideline, and that's just in the bins. at the top of the bins, at about a redshift of 0.5. So this will be really transformative in the way you can start to analyze the extragalactic medium and the CGM. But I would say that my continual observation of the escaping ionizing radiation from the redshift of 0.3 to 1 are a real driver for HWO far UV capability. I'll show you why. Here I've got a bunch of models of L-star galaxies as a function of redshift. So here's 0.3, 0.5, 0.7, and here's 1. And you can see that there's an enormous amount of information far ultraviolet going down below 1200 angstroms as you go further out. And one of the things that I'm very interested in is whether or not the EUV radiation recovers as lambda cubed as you go to shorter and shorter wavelengths. So this is the ionization cross section writ large on the EUV radiation coming out of star-forming galaxies. And the different levels here are expressed in terms of the escape fraction of the Lyman continuum coming from these galaxies. And so as you get down here to the lower end, you can see that actually the flux starts to recover as you go to shorter wavelengths. And that would be considered a Lyman continuum dropping. And people have always, relied on the dropout to determine the redshift of these things. But there may be things that come back and reappear at shorter wavelengths. I'm very interested in finding out if that's true. This is important, say, for understanding how the universe came to be ionized. If when people tell you that the universe is totally ionized, that's a lie. The universe is not totally ionized because you are here. It's kind of obvious. But yet, there's this sort of paradigm that people talk about. There's a whole lot of LUV science that has been gone over in pretty good detail over the past week. I'm not going to get into that. But what I am going to give you is a way that we do a metric, a Lyman continuum yield metric, as an example of how we take spectroscopic modeling and try to determine how many objects that we can actually see. So here are effective area curves for the far ultraviolet. We've got the state of the art of cost in the G140L. Here's views way down here. Here's Havex and Lumos at the 8 meter and the 15 meter. So we do this calculation by taking the effective area, by calculating the total raw area, and folding in mirror reflectances and detector quantum efficiencies, and then ultimately you have to put in what the astigmatism of the spectrograph is. And then you have to worry about backgrounds. So yeah, there's Lyman alpha around Earth. We're going to be at L2, but there's still an interplanetary Lyman alpha that we'll have to contend with. And that's going to give a limit to what we can detect. And it depends upon what direction you're looking at as well, because it has to do with Lyman alpha from the sun scattering off of neutral hydrogen that's streaming into the solar system. Did I go the wrong direction? Yes, I did. Okay, so then you can take that information and fold in your backgrounds, and then come up with what I like to call the background equivalent flux. And that tells you what your ultimate limit is in terms of what you can possibly detect. And we're talking about with reasonable assumptions. Here's Havex with a resolution of about 400. Resolution of R of about 500 compared to a similar thing for Lumos 8 meter. Those designs actually came out to be about the same in the background equivalent flux because Havex had fewer bounces. So there's room to maneuver in your design. We're talking about things down at unheard of height fluxes 10 to the minus 20, which blows my mind. 32 magnitude, and that's a wonderful thing. So then, if you know what your density of sources on the sky are, and you just take that by inverting luminosity functions that have been garnered from Galax and other places, you can come up with a cumulative number of samples of objects that you've sampled to a Lyman continuum limit of X escape fraction to 5 sigma in 10 hours with a 2x2 arc-minute lumos. And these little circles here indicate the limit we can place on the escape fraction. The big ones that indicate 1, and the little ones that indicate 1%, which is sort of spans the range of what we think these things are doing. And then you can get a the total yield, the cumulative number sampled to an interesting number, which is escape fraction is less than 10% in, say, a 100-hour observing program as a function of ratio. Okay, so this is the sort of the basis of how you would go about developing a metric of yield of your sources for the instrument that you're trying to build. And you can tweak, your reflectivities and the resolution of your spectrographs, and the design of the astigmatism and all those good things. And you can carry out these calculations for not only just Lyman continuum, but any kind of spectroscopic observation you want to choose. Okay, so just to go into the UV coating technologies, back in the day, I spent my youth doing silicon carbide over aluminum, which was very limiting in this bandpass. It only had 40% reflectivity, but it was better than the iridium or the osmium coatings that people were using on, say, Hawkins ultraviolet telescope. Of course, Hubble used magnesium fluoride over aluminum, and you can also use lithium fluoride over aluminum. It got kind of a bad rep because Copernicus had a motor that slimed their mirrors pretty badly, and Copernicus didn't really produce as much as they would have liked it. Of course, one of the very first space telescopes, and you could have the lesson learned that you had to do something about your contamination control. Recently, Manuel Quijada has been developing hot deposition processes that have improved the reflectance in the far ultraviolet of magnesium fluoride over aluminum and lithium fluoride over aluminum. He calls these E-LIF or E-night fluoride. But there's been a trick that's been developed that if you use a very, very, very thin layer of mag fluoride over, say, an E-LIF coating, that you can alleviate the sensitivity of lithium fluoride to water vapor. And this capping layer is grown by an atomic layer deposition process that they developed at JPL. And they basically have been coating the E-LIF mirrors at Goddard and then shipping them across the country. And then we go ahead and do the ALD deposition there. Maybe not ideal, but it is a very robust process. And then I'm going to go into a little bit about this new technology that Manuel is developing at Goddard about the reactive vapor deposition, or called the xenon lift, which also alleviates this sensitivity to humidity. And this is for Aki. Okay, she said on the room, great. Okay, Aki, this went from 2.5 microns out to 0.1 microns. Here's the reflectance in comparing the aluminum mag fluoride with the extreme E-LIF mirrors. There's this process, the xenon fluoride process. It's sort of interesting. you deposit your aluminum on glass, you then expose it to xenon fluoride. That grows aluminum fluoride coating, a very thin coating right on top of that. And aluminum, of course, will oxidize if you look at it cross-eyed. But then you can go ahead and do a lift deposition on top of that. And then this is the thing that they don't quite understand. You go ahead and re-expose it to xenon fluoride again, and it stabilizes the lift coating to humidity degradation. And that's something they're working on. They think that has to do with stoichiometrically correcting the surface layer of the lithium fluoride, making it more passive. So these are stability measurements. I won't go into that. But this other technology of magnesium fluoride over the extreme lift fluoride has been pioneered by Brian Fleming. He's flying it on the Sprite mission. And this is a plot that shows there's no degradation from 1,030 angstroms to 1150 after 4 weeks of aging at 40 to 60% humidity. So it was a very stable process. And this is in existence. It's going to fly. We're going to get some data on it. This next part is, I believe, Paul's. No, this is me. Do I want to skip this? Yeah, we'll probably skip this. It just has to do with you've got phase, surface reflectivities are hierarchical broadband by 1 or 2 deformable mirrors placed sequentially, and non-uniformity in the mirrors is an issue. It will create a broadband noise floor. State of the art seems to be about 0.25% in terms of surface quality over a 6-inch surface or so. But it mostly seems to be a problem for the coronagraph, short word about 2,500 angstroms. Polarization is an issue. We don't really know what the polarization of these films are. And of course, transmission efficiency is paramount in the coronagraph system. So there, sorry.
All right, so I'm going to bring up some issues that are being debated, being discussed, just in the interest of transparency, so you guys have some clue about this. So the first of it is the polarization issue that Steve just talked about. Recall that one of the issues that we had to deal with both the Habeck and Lugois studies was this so-called beam speed limit, right? This idea that there will be differential polarization at a reflection point on a mirror surface if you exceeded a beam speed of about f2.2. This was Jim Brackenridge's work that went into the studies. So we know that there's a sensitivity polarization, and we know that this is an issue that we have to worry about because it matters for the coronography. In addition to that known boundary condition, there has been, recall that Habeck's was and HWO is likely to be an off-axis system. So for polarization issues, you would really like to have a completely axisymmetric system, right? So that your off-axis terms in the Miller matrix are small, or at least well understood. But that's not what we're going to be doing. So there's been some concern expressed about polarization-induced aberration terms from an off-axis system for something like what we want to do with the Habitable Worlds Observatory. And there's a number of different ways to potentially correct this. The aberration terms are primarily astigmatism and tilt. And these translate into potential issues that they provide, unfortunately, non-zero cross terms in the Miller matrix. And they will produce, they impact the light, the intensity of the light, but they produce huge phase errors in a way that is apparently not wavefront correctable. You can put a polarizer in the system, but it still leaves those cross terms in place. And there is contrast degradation due to those aberrations, and which becomes more pronounced at short wavelengths. So this is really an issue for the ultraviolet coronagraphic channel more than the other ones. Now, the mitigation of this is that we can select UV targets that are at larger working angles because you can work primarily at something like 12 lambda/d, which is like 100 milliarc seconds, to mitigate the effect of these polarization terms. And this is an illustration from John Christ for the HAVEX design. This is the thing that he had most to hand that he could model with. The size of the wavefront error, at least the phase of it, getting larger as you go to blue wavelengths, and the amplitude is less of an issue. But these are the kinds of polarization. Okay, you can't even see the title. We can do the trick here. These are the kinds of aberrations, some of them down the diagonal of the Miller matrix, some of them off-axis terms that are field dependent in both amplitude and phase. And this was work that John Christ did, and then this was work that was presented at JPL recently by graduate student Jaron Ashcroft from the School of Optical Sciences in Tucson, where he was looking at the Lugois-B study or design, and also indicating these very field-dependent, non-uniform terms in polarization aberration space. Now, one of the things that Jaron presented was the idea of crafting what's called a C-plate to offset this by using multi-layer coatings that had variable thickness across the surface of the mirror. And this can produce the kind of terms that can potentially offset the degradation in the polarization aberration. This is a little bit tricky because now you're not only worrying about deposition of coatings, but you're now varying the thickness of those coatings as a function of position of the mirror. So anyway, this is something that's being discussed within the certainly the ultraviolet coronagraphic channel group. Another issue that came up and Stephen mentioned was this issue of mirror coating uniformity. A few months ago, there was some discussion coming from Laurent and others about how well the mirror reflectivity uniformity had to be delivered, and that those worst case numbers could be as tight as 0.1%, which is actually exceeding the state of the art that Stephen mentioned. And this could be across a one mirror blank or indeed between adjacent segments. So this could potentially require a new way to do deposition that is not ballistic in any way, that is as uniform as possible, and that's where things like atomic layer deposition potentially gets you where you need to go. However, in the last couple of weeks, John Christ has looked at the coronagraphic tolerance on intersegment pupil reflectance uniformity. He was primarily using the U-sort pattern and found that it was much more forgiving at like the percent level. And we can do that. So the correspondence from Laurent, enjoying himself in Grenoble at this particular moment, was that this provides a much more tractable problem. You can place the deformable mirrors in such a way to offset the impact of that non-uniformity. However, the tricky bit is that where you put the DMs for the primary might be slightly different than where you put them for the secondary. So the actual impact on what that specification needs to be about uniformity may need to be tuned and traded and figured out exactly what that might end up looking like. So it's something we need to keep an eye on, but it's certainly not 0.1%. So that's 2 thumbs up right there. Okay, and then another thing that Pim talked about in his talk earlier this week was some of the boundary conditions for this ultraviolet chronographic channel. The use of an IFS requires a lot of pixels across a point spread function, and that means that detector noise becomes the big driver for the noise term in the signal to noise calculation. Therefore, there is potentially a gap here, a need for development of detectors with much better dark noise performance. In terms of wavelength coverage, we appear to be driving towards a blue end cutoff of about 250 nanometers. There are benefits to going to 200 in terms of oxygen and things like that, but the discussions that have been going on, at least within the UV coronagraphic group, is that the return that is afforded by that step is arguable. So I think that's sort of where we're floating right now. This isn't a done deal. This isn't fixed in stone yet, but that's pretty much where we're floating right now. Now, anybody that's worked in the ultraviolet knows that there's a lot of losses involved with reflective systems with the ultraviolet. And Penn did a calculation that he presented the results of this week about particularly low throughput at the back end if you have a design that has 15 reflections. That's because this is the design that he was using, which is borrowed from the XOC design. We may need to go to a much simpler design on the UV coronagraphic channel. But the impact of the low UV throughput, thanks to the good efforts of Carl and Eric, is that there's still a reasonable number of targets, even with that lower throughput, that we can get to with a mirror the size that we're talking about with HWO. So that's good as well. Anyway, and then you wanted to.
All right, Steve, keeping folks in their coffee.
Okay, I know, but I just wanted to point out, I just wanted to throw this out here. Back of the envelope calculation. Hold your question, we'll do it offline. For the counts, for a 30th magnitude planet, and I'm getting in, after you go through the whole thing, that in 1,000 seconds, you can get a signal to noise of 8 if you're down at a contrast of 10 to the minus 10, which is what the 25 is. 25 magnitudes lower than a 5th magnitude. So is that good? Is that bad? Is that optimistic? Let's talk about it.
Suggest that we have these discussions.
We drop quotes.
Okay.
I think this group will benefit from hearing, because there's a polarization uniformity issue due to the metal layer about whether or not you have 4 or 5 reflections. And that happens when you deposit aluminum layers and you get micropolymer structures in it. So this has never been measured for a flight light coating. It's possible that it's okay, but we just don't know what the state of the art is. And so it's also possible that this is a tech gap.
And in fact, it's on the bottom line of my tech gaps down here in red, but understanding polarization.
5 seconds. In the UV, we might not need the IFS for the ozone detection. Photography channels might.
True. Yes.
Well, clearly, this has sparked a lot of ideas and discussion, and but I also know folks plenty of coffee. So I think, you know, with tech problems and everything else, we're running a little late. Steve, you were saying, you want to give folks till 11:05,
11:10.
11:10. All right.
I hope it turns into something. They're doing a lot of stuff about like filling out land sites for future missions.
Sorry. Yes. That's great. Do we know how to fix that?
I can get
There's a door at the sign that says get to room 417 here, so you go through the stairway.
Okay, thank you.
Can you hear me over the noise in the room? I can hear you. barely, but that's good. I think when there's no other.
Yeah, I can barely hear you just with the noise in the room.